this is why this type of style of algorithm kind of breaks down, which is, first, let's ask ourselves, what is the worst possible case of this algorithm? Well, the worst possible case is we jump by 10%. We're still larger than the current value. We still need to keep jumping forward. We need to keep looking. We jump by 10% again. It's still not there. We're still large. We're still larger. We're still larger. We go all the way to the end of the array. We're still larger, which means we have some portion of the very last bit of the array unsearched, approximately 10% of the last part of the array unsearched. Let's now walk through that last portion and look. It wasn't there at all. It was larger than every element in our array. We've totally failed. This sucks. So what is the running time of something like that? Well, the problem is we used n in our jumping, right? We jumped by 10% of n. So that means we're going to do 10.1s. We're effectively going to do, what is it? We're going to do, what is that? 10 operations of jumping. There you go, sorry. 10 operations of jumping plus 1.1 of n, right? Because that's effectively what we're doing right here. So if we denote that in big O, what is rule number 2 of big O?
Ignore constants.
Ignore constants. So bam and bam. So what is our running time right now? It's still n. Isn't that just emotionally defeating? This is still way more efficient. And if you can do something like this, obviously it's much better than linear searching, right? Practically speaking. But theoretically speaking, if your elements go from 100 to 1,000,000, your algorithm is going to run that much slower, right? Whatever that number is, I should have chosen a better one. 10,000 to 1,000,000, your algorithm is going to be 100x slower, even though it's still 10 times faster than your every single index. And so that is problematic. We didn't improve the algorithm, we just improved it practically speaking. So what happened if we could jump differently? So how can we jump differently in this? Well, let's do another thing. Well, what happened if we just jump to the middle of the array, right, and say, hey, middle value, are you equal to v? If it's not, well, then we can check only 1/2 the array. If it is the value, awesome. So let's just say that our value is larger than this value. What do we do? Well, if we just simply linearly scan back this way, well, then what happens? Worst case, 1/2 of n. Well, then you can say, well, let's just do it one more time. We could half it again, right? Okay, so let's just half it again. So now we are only looking over half the space to 1/2 n. So we half it. We're at 1/4 of an n. And if it is larger or smaller, we could then scan. Well, again, what's the problem if you scan at any point? You drop the constant. It's just simply linear. So we can't do that. We can't scan. So what we could do instead, though, is we could, oh, let's see, we could do another one of these xi equals v. Oh, it's not? Well, we could then half it again, right? So let's go here, here. We then half it again. We could go here. This is if we chose a really small number. And we could keep on halving it until either there's no half left to look at or we find our value. And so let's think about how that works. That means effectively we'd have an array of size n, right? Then we half it. So now we have a value space that we're looking at that is really 1/2 n. Then we half it again. So now we have a value space. I'm just going to start writing like this. That's 4. Then we have a value space that's 8. And we have a value space that's 16. And it keeps getting smaller until a specific condition is met. Or in other words, n over 2k equals 1, right? So let's do, this is the most mathy part of the whole course we're going to do. So let's do the classic multiply both sides. There we go. Or in other words, n equals 2k. And of course, for those that remember their logarithms, you can say log of 2, whoop, let's see, of n, whoop, equals k, right? Log of base 2 of n equals k. Or in other words, our running time is log of n, right? Because until we get down to 1, we have to keep halving it. So we're going to half it a log of n amount of times. So practically speaking, if our array was 4,096 and we half it, we'll have 2,048. Then we'll have 1,024, 512, 256, 128, 64, 32, 16, 8, 4, 2, 1, right? And what is the logarithm of 4,096? It is 12. How many steps do we do? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? At that point, you don't technically count the first one. I counted wrong. So this would be the 12th position because that's the starting position. You didn't half that one to get there. You get the idea, though. There you go. So you do 12 halvings to get to 1. And so at that point, you would know whether or not the value is in the array. So the worst case situation is when the value is not in the array and you have to halve it over and over again till the end. You will do a log n amount of halving. So this type of searching is referred to as binary search. Does that make sense? Binary, either 1 or 0, right? There's only 2 possible states. Technically, I mean, in real sense, it's kind of like a trinary search because there is also, it is the value, the happy case. But in this case, it's either it's this side or it's this side, right? You're always splitting it in half. You're always traversing down one path of execution. So let's look at this. Blah, blah, blah. Oh, yeah. Another good little trick of Big O, by the way, is when you half the input at each step, it's either log n or n log of n, right? So just remember that. That's depending if you're scanning that input or not. We're not scanning. We're only looking at a value and then dividing it into half. Looking at a value, dividing it in half. We're not scanning anything. So that's usually a pretty good trick to think about. So this is binary search, greatest algorithm ever. So now that we've kind of written it on a whiteboard, we could implement it. But first, what I'm going to do is I'm going to probably do it a little bit nicer this time. Let's try to do it and do it in a sense that makes it easier to translate to code. All right? So let's think about it more in kind of a pseudocode type sense. We know we're going to half the array. We know we're going to look on either side. We know we're going to do this, so let's do this, a little bit better. So if we think about it, we could have a function that has search that takes in an array, and maybe it has a low and it has a high, right? This is the space in which you need to look into, right? That makes sense. And so what we could do is we could do a loop until some sort of condition happens, right? What would be a good condition that would happen? Does anyone have an idea?
Comparing to the low or the high?
Yeah, exactly. When the low and the high effectively become each other, we are done, right? Because that means we've halved our space to the point where we can no longer have our space. So that's a good thing to kind of remember, conditions always. But let's just kind of walk over this in a more practical sense. So if we start here, what we need to do is we need to go from our low to our high and find the middle point. All right, so that's pretty easy. Let's just write some pseudocode. All right, midpoint simply is going to be low plus high minus low divided by 2 and the floor of that operation. Right? That makes sense. We're getting the middle point because if we're starting from a middle position, we're going to need to make sure that we adjust where we're at. That's why we do the low plus, and then we need to just look at a specific space. So we get the midpoint with the offset. Awesome. We're good to go. So then we need the value at that point, right? So we can do something like array midpoint, right? So we now have the value. All right, awesome. So what do we do in our 3 conditions? Does anyone know what the 3 conditions are? Condition 1. Value is the thing we're looking for, right? I forgot to put this in here. We'll just call it n for needle. There we go. If value equals needle, well, we can return true in this case. We'll just make it simple, right? We're going to just return true. We've found the value. It does exist. Here you go. We could return the index if we wanted to, which would just simply be that right there. Doesn't matter. All right. Or we have our value is actually larger than the midpoint, right? So what does that mean? We're looking at this position right here. What that means is our value is larger than this position, which means that it's larger than everything on this side, which means we simply need to only look on this side, right? That makes sense. So we will simply have to do something. We need to do something to be able to do that. And the easiest way to do it is just adjust our low, right? Our low should equal the midpoint plus 1. We don't need to consider the midpoint because we already know it's not the right value. So we just adjust our low end and put it right in front of where the midpoint is. Else, we can say high. We now need the else condition is that our value is actually lower than the current value, which means that we need to go onto the lower side. So our high needs to equal our midpoint. Now remember, I usually, whenever I do things, I, for the most part, will do something that looks like low is always inclusive, high is always exclusive. You know, always have these things in your head, or else this +1 right here is going to just eat your lunch. You're always going to be off by 1. Things are always going to break down. Always come in with a plan, or else it destroys you. And that's pretty much the extent of the algorithm. Now all we need to do is just effectively come up with our exit condition of this loop, and we've done it, right? Right. So our exit condition can be as simple as this. Let's use the Lord's loop, a do-while loop. I just like to throw those in there because they're funny. Anyways, so there we go. Do-while. Low, whoopsies. Low is less than high, right? We just keep on going until we finally come to a crossing point, because once we come to a crossing point, we're done. They're going to always keep getting closer to each other right here. So we'll know that will eventually happen. And if we get here, we can just simply return false. Doesn't exist. If you were returning the index, you could do a sentinel value of -1. That's what it's called. It's called a sentinel value. Pretty fun. I don't know why I always think about the matrix with sentinels. I don't know why that makes that association, but it just does. So there you go. That is effectively the entirety of a pseudocode version of binary search. Does this all make sense? Normally why, oh, we got one question.
Yeah, shouldn't it be less than equal to high?
We don't want to do less than or equal to, because if you think about it, see, this is the classic. This is an off by 1. This is another off by 1. What does this mean? It means that low is included, but high should not be included. So if we include 1, but we should exclude 1, what does that mean? It means we shouldn't use 1, right? Because it means that our pointers are actually behind each other, is what that really, really means. In other words, if we're at some position, we'll just call this thing, xi, we have a pointer that says, hey, I want to start here, and then our end pointing says, hey, don't cross this line. So it's like fundamentally in a broken state, and so we don't want to look there. So that's how I always think of it, is I just have to have my off by 1s really strong, or else I goof it up. All right, so now that we've done that, actually, is there any questions?
This is all under the assumption that the array is sorted, correct?
It's all under the assumption that the array is sorted. You can never do this on a non-assorted array. The reason, again, is when you come back up to this part, when you come to these two conditions, it has to be able to make the assumption that if I am larger than the current element, then the rest of that side of the array, the left-hand side, is all lower than me. I know that for a fact. Everything over here could be larger or lower than me. I don't know that yet. But it reduces your search space by half each time, because you can make that single value statement. And so since we did that, let's do, of course, the greatest thing ever. Let's go over to our coding machine, go back to day 1, and look for, binary search. Oh, yeah, look at that. So now we can implement binary search right here, right now. So notice that we're given a haystack and a needle again. So as always, let's start off, of course, with the Lord's loop, a do-while loop. You can just use a while. You don't have to use this. And let's create a let low equals 0. Whoopsies. And a high, I'll just keep them the same naming convention as my pseudocode. A high equals the haystack.length. Awesome. So now, again, we need to grab the midpoint. So let's go const m for midpoint, math.floor. And we'll do low plus high minus low, divide by 2. I put that little note, don't forget to divide by 2, because when I programmed this, it took me like 3 minutes to realize I had a bug because I forgot to divide by 2. Don't forget to divide by 2. It's very, very important. Const value, of course, is going to be haystack. M, you're going to see this a lot in algorithms that they use single letter variables to denote everything. I'm just kind of following the pseudocode style, so that way it's a fairly easy direct translation from this into here. Normally, program with good names, but in this case, we're just going to keep it like that. All right, so if value is equivalent to the needle, we have found it, right? I'll take that down here and do a little false. There we go, and we need to come up with a nice condition right here. As of course is while low is less than high. All right, so our three conditions, of course, are going to be when value is equivalent to needle. We found it. Awesome. Let's return true. But if value is greater than needle, that means anything to the right-hand side is going to be greater than mean. I'm already greater than at this current point, so the rest of the right-hand side is going to be greater than. So I want to reduce the high side to this point and exclude the midpoint. So high equals midpoint, because remember, high is exclusive, low is inclusive. Awesome. Let's just cut and paste that. So we can reverse the condition, or we can just do an else statement. We'll just do an else statement to make it simple. Now remember, what this means now is that our value is less than our needle, which means that we need to search on the higher side, right? Our needle is greater than our value. That means if we're going to exist in this array, we're somewhere in the greater side region. So low equals midpoint plus 1, because again, drop the midpoint. You don't want to look at the midpoint again. It would be silly if you looked at the midpoint again. Just having these conditions all in your brain, long as I've done this all correct, we should be able to see this thing go first try. Okay, let me just make sure that I've actually done this correct. NPX, just binary. Oh, that is not how you spell binary, is it? Come on. Oh, okay, well, we have two operations in there. Don't look at the second one, compare binary tree. You're not actually supposed to see that quite yet. So let's pretend the man behind the curtain doesn't exist. Look at that, our binary search actually worked. It was first try. All right, there you go. So I don't think I put this in my presentation, but one of my first interviews at Google, they made me code binary search in Google Docs. It was terrible, and I had +1, -1 issues all over the place. I didn't come into it with a really clean idea of exactly what needed to happen. This algorithm is actually pretty simple, right? Like, that's not a hard amount of code to do. It's, it's really only, 7 lines of actual code. The rest is all spacing, or it's like nothing, right? Initialization and spacing. So it's actually a pretty simple piece of code. It's just being able to focus on this and do this correctly. Do we have any questions?
Just a quick thing. In the repo, I couldn't see the day 1 folder. Do we have it there? I just see the test folder in the repo.
Oh, so it is. So what editor are you? So the question was, I can't see the day 1 folder. What's happening? What editor are you using?
I'm using Visual Studio Code.
Okay, so code may is it hiding get ignored folders?
I'm not sure about it. Is that there in the get ignored?
It's a get ignored, so that way you can generate a lot of them and you don't have a huge amount of uncommit changes. So if you're using Visual Code, I don't use code. I didn't know that, but if it hides ignored folders, you're not going to be able to see day 1. All right, so let's go on to the next part. So I'm going to actually give you an interview question that I had at my first job. This involves arrays. It's also a question that I happen to have in computational theory, which I thought was fantastic. Given 2 crystal balls that will break if dropped from a high enough distance, determine the exact spot in which they'll break in the most optimized way. Often you'll hear this something like, you're in a 100-story building and you have 2 crystal balls and you want to find out which floor do they break. So what's the most efficient way to do it in a 100-story building? This is just the generalized version of the exact same thing right here. So let's do the generalized version, because we're computer scientists. We generalize. We're not going to do the weak version. So let's discuss our options. We right now know of both linear and binary searching. So let's kind of talk about them and their associated time constraints. So if we have you can think of it like if we generalize this problem. Really, when you really think about it, what it is, it's an array full of falses, right? That at some point it becomes true, and from there on out it's true, right? And we're trying to find where is this midpoint, or where is this point? It doesn't have to be mid. There's just a point in which no matter how much higher you go, your crystal ball breaks every single time. There's a point before where it doesn't break. Now, despite what Elon Musk says about the Cybertruck, if you drop this crystal ball over and over again, it won't break. I swear, that was a great joke. We just made that one up. I feel very good about that. All right, so what we want to do is find this in the most optimized way, right? And so if we start off at 0 and just linearly walk, yes, we will find it, correct? We will eventually get to true. It will break. But we are given a constraint, and we really didn't even use our constraint, which is we have 2 crystal balls. I apparently can't spell crystal. We have 2 of them, right? So therefore, we should be able to do something more efficient than that, right? Because if we linearly walk and find t, what is the runtime of the algorithm? Imagine in your head what you're going to write. You're going to write a for loop, right? You're going to write a for loop over the space of the array checking every single time. It's a loop. Trick, look for loops. There's a loop based on the input. Boom, linear, right? It's O of n. Very, very simple to see. Okay, we're like, whoa, 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 whoa. We are so much smarter now. We already know something. This array's ordered, right? If we break it down in the most orderly kind of way, it's this, right? It's a bunch of zeros until it's a bunch of ones. We're so much smarter than this. We can easily do this. So again, we have an array. We jump to the middle. And we're like, hey, x of I, are you true? And it's like, yes. Oh no, what just happened there? Well, one of our two crystal balls just broke. And so therefore, what do we have to do with the remaining one? We have to linearly walk from our last known good point until we hit a bad point. And if we walk 1/2 of n, what's the running time of that? Remember, rule 2. Yeah, drop the constants. Boom. Oh, dang it, I drew on the line. Bam! Oh, right, there you go. You've just dropped the constant, and it's back to n. So both of our searches suck, right? Like, neither of them work. I really wanted to work this one in here because specifically during the interview, the interviewer did not know the generalized answer, and when I just said it right away because I was so stoked, they said, well, that's not the answer. I said, it is the answer, and here's why. Oh, this is so exciting. So what do we have to do here? Well, the reality to the answer is this, is that we need to jump in such a way that isn't some portion of n that means we have to walk some portion of n. We need to be able to jump by a fundamentally different unit. Does that make sense? So normally what we did in binaries, we'd cut the space in half. That makes it really, really efficient. But in this case, we're jumping, so we need to do something different. So here's what I propose. We jump the square root of n, the squirt of n, right? And so that means we're going to jump a square root amount of times until it breaks. And if it breaks, we have to walk backwards to our last known good point. and find the point of braking. If we walk back and we have to walk forward, how much are we going to walk forward at most? The square root of n. So what is the running time of having to do a square root of n plus a square root of n worst case? Right? Because we could have to do a square root of n jumps until we're off the board, back it up by square root of n, and walk square root of n. So what is the time of this?
Square root of n.
The square root of n. Look how fantastic that is. We actually did it. Now, you don't have to write it like this, because of course you can rewrite that as the 2 square root of n, or of n, and so what do? You drop the 2. So pop, 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 pop. We have just come up with a new running time that you probably will never see again, but this is a fantastic little exercise, which is we now have just broken down a search problem without doing a linear search. And I think that that's really kind of a cool thing. I love these type of tricks because often they'll expand my mind for me to be able to use this in other areas. If I see something that I can't use, say, a priority queue, which we'll talk about, and I need to be able to search in such a unique way, I have one more trick inside my bag. And it's always good to have one more trick inside the bag. We'll implement it because it's so exciting. Oh, I really think it's exciting. I think this is a good exercise to go over. So again, open this up, search crystal balls. There we go. And so I'm going to pass in the breaks array, Boolean, and you're going to return back out the index into this array. So remember, just like our algorithm, we want to jump by the square root of n. And so how do we do that? Well, it's pretty straightforward. Const jump amount will equal math.squirt breaks length, right? But we can't really use just that because what's the square root of 3? I don't know, right? I'm not that smart, so therefore let's become that smart and let's use the floor unit. Let's assume that the array is big enough to have a square root. There we go, right? It's going to be effectively 1 for 3. There we go. So we now have our jump amount, the amount we want to jump. So what's the first step? We use our first crystal ball to see where does it break. So I'll go like this. Let I equals jump amount. Oh, we have a question.
Yeah, why suddenly square root and not having like before?
Okay, yes. So I did the worst case right here. So here's why having doesn't work. If you jump to your middle element and your ball breaks, what does that mean? Well, that means you only have 1 left. Therefore, you need to start from a last known good position, which is 0 in this case, and walk to half of n. Half of n, walking half of n, is still linear time. We want to improve linear time. And so that's why it is better to jump by a different amount. So jumping by the square root of n means that we will at most walk square root of n. Or in other words, the worst possible case is square root of n amount of jumps until we're off the array, go back square root of n, and walk square root of n. Does that make sense? Whereas the worst case having is that you have to walk half the array. There we go. So I is the amount we want to jump. We're going to start at the first jump because it will make sense. For I has to be less than brakes length, I plus equals jump amount. There we go. And so now we just simply try to wait until we brake. So if brakes I, then brake. Oops, I just replaced that. There we go. Now we do exactly what we said. We find the point where it brakes, we walk back, we jump back square root of n, then we walk forward square root of n. So I minus equals jump amount. There we go. And now we've just jumped back square root of n. Now we just simply need to walk forward square root of n. So for let j equal 0, j has to be less than jump amount. And we'll go like this. I has to be less than brakes length, just in case we walk off our board. We don't want to walk off our board. And then we can just go plus plus j. Awesome. So now we're going to make sure we walk maximum a jump amount of steps. If brakes I forgot one thing, plus plus I, there we go. If we find the breaking point, there we go. We can literally just return I at this point, or we can return -1, right? There you go. That should be the answer. I always get so nervous about to run this. Here we go. 2. I think that's all we have to type. Oh my goodness. It worked out again. So there we go. So here's the a simple code, which again, we did it in the exact same steps. I'm going to jump over here. We first walk by the square root of n, jumping square root of n at a time. Exact same thing you see right here. We set our initial jump point or our initial point to the square root of n. We then check for breaks and jump square root of n. We jump back a square root of n. Then we linearly walk forward at most a square root of n until we find a break. At that point, we either return I at this moment, which is the index in which it breaks, or we return -1. Hopefully that all makes sense. It's a pretty fun algorithm to kind of think of. I think it's a really kind of a challenging one too, because it just changes kind of how you view it. And you never know. I was asked this question. Maybe one day you guys will get asked this question. Likely not, now that it's on the internet, completely ruined it. But it's a fun one. So I've already said I've had this one. Oh, look at that. I even did the binary search in Google Docs. You know, it's shocking how many times you'll get asked to do binary search at Google. They just ask that question all the time. So, you know, come prepared. Be ready. All right. All right, so let's take a breath. You get it? Good pun. I think it's a great pun. I'm sure there is a lot of questions. This is a great stopping point for any questions we can have at this moment.
Can we traversal cube root of n instead of square root of n?
We could travel a cube root. I wouldn't know how to. I wouldn't know what the running time of that would be though, because that means you'd also have to hop cube root of times, which is a higher amount of hopping.
Cube
right?
root is smaller than the square root of n. Right?
It is smaller, so your jumps become progressively smaller. I don't know. I don't actually know what that proof would look like and why it would be faster or slower. To me, it seems like it'd be slower.
What if we go more than square root? I'm just trying to figure out why we have chosen square root of n.
Square root of n? Well, the square root of n, it just is the only way we can change this from nonlinear running, right? Because if we use a binary search, we still run into a linear problem. If we jump by some portion of n, we're still running linear. So if we want to get sublinear, we cannot get to log. But if we just do a cube root, if we just do a root, then we get the maximum amount of jump, right? You get the maximum amount of distance with a still lower running time. As you increase, obviously, your root level, the closer you get to a linear run, right? So if you do the quad root, then you get to the point where you're practically jumping by 1, right? Then you do the next root, you are definitely jumping by 1, if not by 0 at that point, right? It just like becomes nothing. So I think it quickly approaches n.
Wishing their college professor was you back in the day.
You know what? I still, if this ever gets back to Montana State University, Brock Lemire's best teacher ever. I model everything after him. He got Teacher of the Year award once. The man was writing he did Carnot maps, he did digital logic, all that. He was writing on the board. He was so excited that when he tried to write, it launched out of his hand and made it all the way across the room. And I was sitting there like so engaged going, this is how I want all my professors to be, right? I want them to feel like they like what they're teaching. And I like what I'm teaching, so I don't want to, I'm showing you how much I like what I teach. Also, of course, you have to do sorting. So normally when you look at algorithms books, it often starts at sorting.